Today you had a chance to look at warm-up number 11, and either you chose the reteach opportunity or the challenge opportunity. We're going to do some checking. First, let's start with the reteach. It says directions. Write the sum of two numbers as the product of their greatest common factor and another sum, 20 plus 40. Well, I know they must be asking more than 20 plus 40 happens to equal 60. That's good thinking. That's probably going to help me do some checking in a little bit. But I do know that it says I want to write the sum as the product. Product really means multiplication. And then it says of their greatest common factor. So I'm going to have to find the GCF in here. And then it talks about another sum. If you remember, when I'm done, I really want this to look like a factored format. I really want the greatest common factor, take it out of both numbers, and their leftover factors in parentheses looking like a sum or looking like addition. Sum means addition, or the result of an addition problem. So let's give this a try. If you remember, there are a couple ways to find GCF, or greatest common factor. Most of us should be pretty comfortable using a tree method. And trees are nice because you don't have to worry so much about missing factors along the way, or factor pairs like we do with a T-chart. So let's try breaking down 20. If you haven't done this yet on your own, you want to add this to your paper now. 20, let's see, that's the same as 4 times 5. And maybe you chose to use 2 times 10 on your tree. That will still work as long as you're giving me good factors as you break down your composites. Well, 4 is not prime, but 5 is, so I'll circle it. 4 is composite, so I need to break it down. 4 could be written as 2 times 2. And if you remember, 2's, even though they're even, they're the only even prime number. Looks like this tree is done. We next need to break down 40. So I choose a factor pair that will get us started. Well, 1 times 40 would work, but 1 is special. We try to keep those off our trees. So let's see here. I remember 5 times 8 will work. 5 times 8 is 40. 5 is prime if you remember, but 8 is composite, so we're going to break it down. 8 is the same as 2 times 4. Well, we'll circle our primes and break down our composites. 4 is the same as 2 times 2, and both of those being prime means my tree is done. With all good trees, we should, yes, chop them down, or maybe line up our factors. So I could say 20 is the same as 2, 2, and 5. And remember, because these come from factorizations, we use multiplication. 40 then is the same as 2 times 2 times 2 times 5. Looks like I have all of my factors here for 40. Next, I want to do some comparing. I want to say, what's the greatest common factor I can make from all of these factors in their factorization? Well, I look for things that they have in common, or factor pairs. There's a pair of 2's. Here's a pair of 2's. And some of you might be looking to circle this 2, but we can't. He doesn't have another pair to go with him, or another 2 to make a pair. But if you notice, these 5's, they match. And even though they're not sitting right on top of each other in factorizations, one came from 20 and one came from 40, so they are a good pair. Well, let's take these and figure out our greatest common factor. I had a pair of 2's. We write it. I had another pair of 2's. Record that as well. I had a pair of 5's. Write that down. And because we're talking about factorizations, we still use, you guessed it, multiplications. Let's see if we can simplify this a little bit. 2 times 2 is actually 4. And I still have this times 5 at the back. Well, 4 times 5 is actually 20. This is great. You just found me the greatest common factor. This is really the number of groups I could possibly make out of 20 plus 40. I could make equal groups. I could make 20 of them. So this really goes into my factored expression. I write 20 as my greatest common factor, and behind it I could record for you the leftover factors, anything that had not been circled. Well, if you look back at 20 and its factorization, everything was circled. What is the only number possible? The only one I can think of that doesn't really appear here but wouldn't really change its value. There's only one number on the planet that I can multiply by and still keep the same value. It won't change the value of 20. The only one would be times 1. Remember, we talk about 1 being special. When this happens in your factorization and there's nothing left uncircled, the only one that will work, you guessed it, 1. Well, let's go back to our factorization of 40. Were there any extra factors? We circled these 2's. We circled this 5. Ah, there's the extra. This 2 is an extra factor. We'll use it in our sum. So again, we have 20 groups of 1 plus 2. Does this make sense? Let's do some checking before we call this our answer. What is 1 plus 2? Oh, you guessed it. 1 plus 2 is actually 3. And this 3 in parentheses is sitting right next to a 20. So hopefully you remember secretly what's happening here. It's a multiplication. So 20 times 3 gets me, the same great answer. You just found me factored form. Or you just took these 2 numbers and wrote them as the product of their greatest common factor and another sum. We can record that here. 20 groups of 1 plus 2. And the tricky thing about this one today is if you didn't use another method, you might be looking here and wondering what is left over from 20. But the only one that will work when this happens, the only number on the planet that will make it true, is 1. Next, you'd be expected to explain your steps down here. So I definitely want to talk about using my tree method. I definitely want to talk about how I found factor pairs, and then I figured out my greatest common factor, or the largest number of groups I could make. And I want to even describe where I found my extra factors that went in that new sum, that 1 plus 2. Where did they come from? Oh yeah, that's right. They came from our factorization. And when all numbers are circled in your factorization, the only factor that could possibly still work or be left would be 1. That's something worth noting in your writing today. Let's pretend you didn't choose the reteach at all. You chose the challenge. Well, hopefully you're up for the challenge because it has something a little bit different. Here it says we're going to solve the problem below. Be sure to show all work. The Math Counts Club had a party at school. There were 20 cookies and 40 slices of pizza to be shared equally. Each student had the same number of whole cookies and the same number of slices of pizza with nothing left over. That sounds important right now. Nothing left over. We're going to use all 20 cookies and all 40 slices of pizza. How many students could have been at the party? There is more than one answer. List as many as you can. If you think back to our work a minute ago, you discovered for us that we could make 20 groups. Well, that could represent 20 students. If there are 20 students, the 1 comes from the cookies. There were 20 cookies. And the 2 comes from the slices of pizza. There were 40 slices of pizza. So one possibility I already know. It comes from my factor trees. I could say 20 students, and they each get 1 cookie and 2 slices of pizza. Here's the trick. You really have to have those factor trees built from the other page if you're going to write this. Okay, so hopefully you already have your factor tree of 20 and your factor tree of 40 so that you can prove this is true. But I'm wondering, what if I didn't have 20 students? Could I have had fewer? Could they have had more cookies and more slices of pizza each? The answer is yes. So what we kind of could do here, we could try maybe a T-chart method. We could maybe even try a ladder method to try another approach and see what we get. I like ladders. I'm going to give that a try for you today. So if you haven't tried a ladder method, I'm going to ask you to copy it down now. Remember, the only trick with a ladder is you have to choose a special type of number on the outside here. Prime. Well, 2 is prime, and it goes into 20 and 40. It goes in there 10 times and into 40 20 times. You actually are looking at an answer right this minute. How many students could have been there? Maybe just 2. And when I split up my cookies, I'm left with 10 cookies for each of them. And when I split up my pizza, I'm left with 20 slices for each of them. That sure does sound like an awful lot of pizza and cookies for just 2 people. Let's see if we can break this down again. Another possibility would be to divide 10 and 20 another time. Looks like I could divide them both by 2 again. 2 goes into 10 5 times, and 2 goes into 20 10 times. Well, this means that there were originally 2 students, but now we've got these 2 more students. This is really saying 2 times 2. Looks like I could have 4 students at this party. And each of those students would get 5 cookies and 10 slices of pizza. Maybe we want to label up here, cookies on the left, pizza on the right. Just might help our organization or our answers in a minute. Well, let's go another time. And before we do that, let's go ahead and record what we found. Maybe we only invite 2 students to the party. Well, when we go back to 2 students, each of them got half the cookies. They each got 10 cookies. And they each got half of the pizza, 20 slices. I think that would make anyone feel a little bit overwhelmed. So let's try the next thing we looked at. We said how many students could be there? Maybe 4. 4 students. If that's the case, each of the students would get, let's see here, 5 cookies and 10 slices of pizza. I'm just using some ditto marks to kind of show you another way of shortcutting cookies and slices of pizza. I'm showing you that I take that thing right above it and I copy it down. Well, is there any other number of students that I could have had? Look at this 5 and 10. Could I split it another way? Yep. They both divide by a prime number. That's 5. Well, 5 goes into 5 one time and 5 goes into 10 twice. If you take a look, I really could say that I had 4 times 5. I really could say all of this. I had 20 students. And each of those 20 students had 1 cookie and 2 slices of pizza. Oh, that's right. I recorded that up above. There's another thing we should be careful about, though. If you notice, 5 goes into these factors down below, or these composite numbers that actually happen to be factors to get us 20 and 40 a minute ago. Another way that we could approach that is probably dividing 20 and 40 by a common factor of 5. Would that work? What if I started my ladder differently and divided by 5? 5 goes into 20 4 times, and 5 goes into 40 8 times. Oh, 5 students could be there. And each of them would get 4 cookies and 8 slices of pizza. Really, you want to see if we're missing any common factors. So maybe a T-chart would have been a better way to go. It looks like 2 is a common factor of both numbers. It looks like 4 is a common factor. It looks like 5 is a common factor. I wonder if even something else would work. Well, 4 and 8 could be divided again. Could divide them both by 2, and 2 goes into 4 twice, 2 goes into 8 4 times. Oh my goodness, if I took this, I could have invited 10 students instead. 2 times 5 is 10. That's another possible answer. If I do that, how much should each student get? Well, 20 cookies divided among 10 students gets you 2 cookies each. And 40 slices of pizza divided among 10 students gets you 4 slices each. A really crazy thought. What if no more than 1 student arrived? Is it possible that only 1 student came to the party? Probably unlikely, but if that were the case, how many cookies would they have to eat? 20. How many slices of pizza? Too many. I'd like you to do some checking, and maybe again you go to a T-chart to make sure that you have all the possible answers, but it looks like we found 1, 2, 3, 4, 5, 6 possibilities at least. These are all possible answers. It says list as many as you can. So if you think of something that I didn't mention here, or you try those T-charts just to make sure we're not missing any common factors, we're heading in the right direction. So how will you explain your work? Well, really, I really hope you think about the most number of students that could arrive. The most number of students, or the greatest common factor that goes into both of the numbers, both 20 and 40, divide by the greatest common factor of 20. But what's the least number of students? If you look back at the top, what's the smallest number of students we had arrive? No, only 1 student. And that would really be the smallest common factor, which we don't talk much about, so that's kind of a funny thing to consider, but only 1 student. When you're doing your writing, I'd hope that you'd explain some different possibilities involving 20 students or 1 student, and maybe explain why I didn't say 8 students up here. Why wouldn't 8 work? I could divide my slices of pizza by 8, but look at the cookies. Oh, that's not a good possibility. 8 doesn't go into 20 nicely without splitting up those leftover cookies some way, shape, or form. And it said, I want to make sure the cookies stay whole. And the pizza slices stay slices. Once you have finished these, either one you worked on, the challenge or the reteach, you're expected to rate yourself. So how did it go? Include in that thinking you're writing. Were you able to explain your steps? If you share them with someone near you, will they understand what you're saying? Will they understand which strategy you used? Well, rate yourself today, whichever you think is true. A 1, not yet. A 2, kind of. A 3, I'm almost there. Or a 4, I got it. Don't forget your name, date, and hour at the top. Just makes our job a lot easier in the grade book, and then you don't have to worry about losing extra points. Once you're ready, it's time to turn these in.